Okay, so let's take a look at um, some examples with some numbers so you can see how this works. So here we have a kayaker capable of traveling at a speed of 4.5 meters per second in still water is crossing a river that is flowing with a velocity of 3.2 meters per second east. The river is 220 meters wide. So if they can travel across the water, still water at 4.5 meters per second, that is the velocity of the kayak with respect to the water. So 4.5 meters per second. And the velocity of the water with respect to the ground is 3.2 meters per second east. And the distance across the river is 220 meters. Um, if the kayak is aimed north, okay, so it's heading north, okay, what is the velocity of the kayak relative to the shore? Okay, so that means width of the river is also north. Okay. So we always kind of start these with a vector statement to see what we're looking for. So we have the velocity of the kayak with respect to the water, the velocity of the water with respect to the ground. So if we add those together, okay, we'll get the velocity of the kayak with respect to the ground. Okay. So we're adding two vectors together. This is north, this is east. So we're going to have to do vector addition here. So we've got we have 4.5 meters per second north. We've got 3.2 meters per second east. So our resultant vector, right, is going to be the vector addition of these two things. So kayak with respect to the ground. Okay. This is a right-angled triangle, so we can just use Pythagorean theorem to add these vectors together. Okay. So that means VKG is going to be 4.5 squared plus 3.2 squared rooted. Okay. And we punch that through our calculator. We get 5.5218 meters. Okay, we need an angle. Okay, so tan theta is going to be 3.2 over 4.5. Okay, so if we run that through, we get the theta is 35 degrees. So the velocity of the canoe with kayak with respect to the ground is 5.5 meters per second. We're limited to two significant digits here. And then we are 35 degrees east of the north direction. So that is our answer. Okay. So again, once we set the problem up, all we're doing is vector addition. Okay, so we're just dealing with 2D vectors again. Okay? So that's always kind of the trick to remember with these kinds of problems. Okay? That was part A. So let's look at the rest of this. So part B, how long does it take the kayak to cross the river? So when the kayak is going across the river, whether it is going still or whether it is being pushed, okay, it's going to take the same amount of time. So because the kayak was going north and the river is going east, okay, those are perpendicular to each other, meaning they don't affect each other. So how long does it take the kayak to cross the river? Well, that's just going to be V equals D over T. So how long does it take, right, in still water versus if it's being pushed? Okay, so that's going to be 4.5. So the speed of the boat with respect to the water. Okay, that's straight line across. And then the distance that's straight across. So 220 over time. Okay. So we calculate that. We get 48.8889, or just 49 seconds. Okay. See, how far downstream does the kayak land? So in the time that it takes the kayak to cross the water is the same amount of time that the current has to push it downstream. So once again, we're just going to do, V equals D over T. The difference is this time we're dealing with the current, so 3.2. We want to know the distance that it got pushed downstream. And we're going to use the same time that we just found. Okay, so we run that through the calculator. We get 156.4. And if we round to two significant digits, that would be 160 meters. Okay. So, right, the time it takes to get across is the same amount of time that the current has to push it off track. Okay. So that's what I mean. The math here is really simple, right? Just V equals D over T. We use that for both B and C, but we have to think about which velocities we're using and which distances we're using and what values we need. So that's what I mean when I say that these problems are tricky to set up. Okay. Part D says, if the kayaker wanted to land directly across from the starting position, at what angle should the kayak be aimed? Okay. So in this situation, okay, they're going to shoot the kayak out, so that 4.5 meters per second. They're going to aim into the current so that the current, straight lines here, they're going to aim, we're going to pick some angle to go into the current so that when the current pushes them back, they end up straight across from where they started. So we change the vector from we're going this way, and we have our resultant vector. Okay. Now we're angling out. Okay, the river is coming across, and our resultant vector is going to be straight across. Okay. So this question is asking us to find the angle. So we just need to find this angle. Okay. Because we're trying to get straight across, that makes this a right angled triangle. And we just need to find an angle. So we don't actually need to do any vector addition here. We're just solving for an angle in a right angle triangle. We have the opposite and the hypotenuse, so we're going to use sine. Okay. So we run that through our calculator and round to significant digits. We get approximately 45 degrees. So they would need to aim 45 degrees west of north. So in order to get straight across, they would have to aim their kayak 45 degrees into the oncoming current. Kayak as normal, and the end result there is that they're going to get further down. They're going to end up straight across instead of not where they wanted to be and having to walk the kayak back. Okay? So they can plan ahead a little bit and get to where they want to go. Okay, let's take a look at one more problem, this time dealing with an airplane. Okay. So a pilot is required to fly directly from London to Rome in 3.5 hours. Okay. The displacement is 1,400 kilometers. 47 degrees south of east. A wind is blowing with a velocity of 75 kilometers per hour. So that is going to be wind with respect to the ground, 75 kilometers per hour east. Determine the required velocity of the plane relative to the air. So this is asking for the airspeed. So how fast does the plane travel? So in this one we know, okay, we've got to get from point A to point B, okay? So we want this to be our resultant vector. Okay? We have to figure out which way do we fire the plane into the wind to get where we want to go. Okay? So we know that the velocity of the plane with respect to the wind and the velocity of the wind with respect to the ground would give us the velocity of the plane with respect to the ground. Okay? So we need this value, the velocity of the plane with respect to the ground. So we know the distance that has to be, and we know the time that takes. So we can just use v equals d over t, and we can find this value. So 1400 over 3.5. And we can get our value of 400 kilometers per hour. And the distance, the displacement was 47 degrees south of east. So the velocity will be the same. And this velocity is the velocity of the plane with respect to the ground. Right? This is the end result that they're looking for. We need to figure out this one. Okay? So what that means is, right, we're going to have to rearrange this equation. Okay? So if we rearrange this equation, we're going to get v, velocity of the plane with respect to the ground, equals the velocity of the plane with respect to the ground minus the velocity of the wind with respect to the ground. And as we mentioned earlier with 2D vectors, subtracting vectors, we don't really have math for that, but subtracting is the same as adding the negative. So v pg plus the negative of the velocity of the wind with respect to the ground. Okay? So the velocity of the wind with respect to the ground is just going to be the opposite, right? It's going to be 75 kilometers per hour west. Okay, so just the opposite direction. So in order to solve for what we need, we're going to need to take this vector here, okay, and add it to this vector here. So 400 kilometers per hour, 47 degrees south of east, and we're going to need to add that to 75 kilometers per hour west. Okay, so VPW equals VPG plus negative VWG. So, right, our first vector here is 400 kilometers per hour, 47 degrees south of east. And our wind speed, right, is 75 kilometers per hour west, because we're doing the negative of the vector. So the vector that we are trying to find is the sum of these two vectors. Okay. So we have to add this vector and this vector. Okay. So I have to break this vector into components. And just like we did with displacement, we can do the same thing with velocity. All the equations work the exact same way. So we have 400 cos 47, and this would be east. The 75 was west, so we would subtract that. Okay. We run that through our calculator, and we get 197.7993 kilometers per hour east. Okay, we do the y as well. So Vy is going to be 400 sine of 47. There is no vertical component to this other vector, so that's it. We just put that piece by itself into our calculator. We get 292.5415 kilometers per hour south. Okay. We have two vectors, a single vector going east and a single vector going south. So we can just make a little right-angled triangle. Right? Vx, Vy, and then the vector that we are trying to find, VPW. Okay. So we use Pythagorean theorem on these two things. Okay. Squared. Okay. So we run that through, we get 353.1361 kilometers per hour. Okay. And then tan theta is going to be Vy over Vx. So theta is going to be the inverse tan of 292.5415 over 197.7993. Okay. And we get the angle to be approximately 56 degrees. Okay. So we put it all together, okay, and we get that the speed of the plane is 350 kilometers per hour, and our angle is south of east. So 56 degrees south of east. So what this means is, in order to get the time that we wanted, in order to fly from London to Rome in 3.5 hours, to cover that distance with the wind speed the way it is, this is how the plane would have to fly. They would have to fly at 350 kilometers per hour, and they would have to fly a little more south than flying actually there. And then the wind speed is going to carry them the rest of the way. So they make their flight in the 3.5 hours, okay, with the right direction. Okay. So hopefully that helps clear things up a little bit more for you about relative velocity. Again, all the math is 2D vectors. The trick to these is always just setting them up, okay? And that just comes with practice.